The goal shouldn't be human level performance. The goal should be superhuman partnership.
People who tour these galleries often say, wow, I had no idea. Many think computing is about engineers and mathematicians. But if you've ever texted a friend or talked to Siri, you know computing is about you. A distant dream of computing has long been machines that can think, act, and reason like humans. And perhaps no dream has been more elusive. How close are we today? We put that question to Dr. Peter Norvig of Google and Dr. Eric Horvitz of Microsoft Research, two global experts in artificial intelligence. Your host is KQED's Tim Olson.
I'm thrilled to be up here on stage with these two fine distinguished gentlemen. Dr. Eric Horvitz is the Distinguished Scientist at Microsoft Research. He is the immediate past president of the Association for the Advancement of Artificial Intelligence, a fellow at the American Association for the Advancement of Science, recently inducted to the American Academy for Arts and Sciences, just back from serving with the NSF, that's the National Science Foundation, where he's an advisory board member. He's got a PhD in AI from Stanford, as well as an MD from Stanford, which is interesting in this field. And he and his team at Microsoft helped create some of the world's first spam filters, of which we are all very grateful. Dr. Peter Norvig is Director of Research at Google. He is a fellow at the American Association for Artificial Intelligence, also a fellow at the Association for Computing Machinery, former head of Computer Science Division at NASA Ames, right down the street, where that was the NASA's senior computer scientist. He's one of the authors of Artificial Intelligence, A Modern Approach, which is considered to be the leading textbook in the field, and about that thick if you haven't looked. His PhD is at computer science at UC Berkeley, so not only are Google and Microsoft on the same stage, we have Berkeley and Stanford. It is indeed Switzerland here today. And if you search in Google for PowerPoint, you will find Peter's one world-famous PowerPoint presentation among the results, and I'll leave that for the crowd for a little homework later. It's quite a fun little treat. So as John mentioned, this dialogue is part of a week of looking at science, and there's science festivals all around the Bay Area. One of the things they're trying to do is try to inspire people into careers in science and thinking more scientifically. You both have a long, distinguished resume. What got you into science in the first place? What lit the spark, so to speak?
So I've always been extremely curious about everything, and I think I was never told not to ask questions. And so you ask one question, leads to another question. I was particularly interested in how things work. I remember asking my dad what God was made of. I was curious about what was going on there. So you have to sort of be really just keep that thread going, and as parents, really, I think, be supportive about streams of questions that might lead to a whole new stream, each one of them.
Yeah, I think I would echo that. So a lot of it is wanting to understand the world, make sense of things, have questions that have answers. And then also I think part of it is wanting to have an effect on the world, of saying, you know, what can I do to contribute something that might actually help someone out there, and seeing the capabilities of being able to apply what you know theoretically to something practical in the world.
Yeah, it's a great theme. There's often a big disassociation between science out there in the quote-unquote real world, but I think part of our talk today will address how that's a big misconception. Peter, this is about AI. There's a lot of lay people in the audience, including myself. How do you define AI for a common person?
I guess the way I think of it is AI is the science of knowing what to do when you don't know what to do. And in some sense, that's, you know, all of computer science is about solving problems, instructing a computer how to do something. But often that's for something that you do know how to do, right? So balancing your checkbook, you know what to do. You add up these things, you subtract these things, there's an answer that you know. And AI is when you don't know. And why might you not know? Well, you may not be able to observe everything. So if you have to drive a car, you have a certain number of cameras and other sensors, and you can see part of the world, but you can't see the other parts of the world. And yet still you have to take an action. You know, if you were writing the checkbook balancing program, you wouldn't think of, well, what about all the checks that I don't know about? Those are out of bounds. But for AI, all of that is in bounds. And then also when you're driving the car, you don't know what's going to happen when you take an action. So if I say, hit the brakes, I don't know if I'm going to stop in 5 feet or 10 feet or 15 feet, depending on how wet it is. And yet still, the program has to know what to do, even though it doesn't know the outcome. There may be other things, like if you're playing chess, you don't know what moves the opponent is going to do. So it's this reasoning with uncertainty and still being able to take the right action. That's what I define as AI.
It's interesting that there seems to be a growing interest in AI. We have a big crowd here. You're actually authoring a course at the moment that has 140,000 students from over 190 countries taking Intro to AI. Who would have thought?
We're up to 200 countries now.
Oh,
so there's
wow.
a couple countries in Central Africa that we've missed. But
Was this a surprise? Did it just...
So we were very surprised. So, you know, we've done this over the course of the last couple of years. I've been more interested in education and what we could do that's, you know, so I've had the textbook for many years and felt that was kind of stale to have these dead pages. And what can we do that's more interactive, more exciting? And so my co-teacher, Sebastian Thrun, and I taught the class at Stanford, the Intro AI class at Stanford last year with an aim at kind of moving it more online. And this year we said, okay, we're going to make this leap to say not only are we going to offer it to Stanford students, but simultaneously we're going to offer a sort of sister class to the whole world. And we were excited to do that. And Sebastian, who's always very enthusiastic, said we could get 10,000 people signed up. And I said, nah, Sebastian, you're crazy. We'll get a couple thousand for sure, but we won't hit 10,000. And then after we sent out an email to AAAI, and after a week we had 10,000 people. The next day we had 20,000 people, and we got up to 160,000 registered. So there's a lot of pent-up interest in being able to take something like this. And it's been great that people have been sticking with it. And we've got, as you mentioned, 140,000 people have at least seen some of the video lessons over the last 7 days. And 30,000 of them have handed in the 3 weeks of homework that we've had so far. So they're working hard.
That's a lot of grading that you've been doing. Yeah.
Fortunately, we have computers to know,
That's good.
to know
That's
what
a
to
good
do
use of AI. That's right.
when we don't know what to do.
So I just made a comment that I think this is a great sign of deep, latent interest in machine intelligence. I think besides some of the noteworthy news items like Watson's success, Deep Blue's success a few years back, the machine intelligence, the vision of artificial intelligence is a long-term vision on the opportunities for where computing is going and might go someday. The work also has, as many people realize, deep implications for what it is that we are. You know, what are our minds like? Using tools and methods and ideas and theories about principles of intelligence to better understand human intelligence. I just get the sense that that's part of the latent interest and excitement about these concepts.
Many of us may not sort of realize that. You think about spam filters, or you think about the latest operating system from Microsoft or others. These are actually under the hood AI, are they not?
Yes, I think that's right. That AI touches you every day, many times. You know, every time you do a credit card transaction, some computer has to decide, is that going to be approved or not? And that's done that way. You mentioned all these decisions made for recommendations. So spam filter, is it in or out of your spam inbox? You go to Netflix or you listen to some music, what recommendations do you get next? what advertisements are shown to you. So sort of everywhere you go, decisions are being made that affect you that are being made by AI systems.
So one of the big surprises probably couldn't have been predicted by Herb Simon and Marvin Minsky and John McCarthy early on in late 50s and 60s was to what extent large-scale amounts of data would serve as critical in some of the applications we're now seeing and theories of what it is to be an intelligent system. The idea of even, I'm sure it was beyond people's expectations, that we'd even be able to collect so much data and have it around to analyze, and the deep role of machine learning from data to predict the future or to infer hidden states of the world that we can't see directly. There were some beautiful papers written in the 50s and 60s about machine learning. Some are quite modern if you read them. But the current trajectory we're on, at least in a large branch of both theoretical and practical applications of AI, is showing us that we can do quite a bit with data. And I know Peter has quite a bit to say about that as well.
Yeah, I think that's right, and we can get to data in a minute, but let me touch on one other thing that I think has changed since the 60s, is just the conception of what a computer is. And, you know, so then with the predictions that Newell and Simon had to go on, they thought of the computers were these rare big things. And, you know, there's a famous quote from an executive at IBM who said, well, maybe there's a worldwide market for 10 computers. And now, you know, most of you probably have 10 computers with you. If you count your pockets and go out to your car and count up the number of computers, you're going to exceed 10 each. So that really changed, and you know, even the visions of the future have changed. You look at like 2001, and HAL is the iconic computer there, and HAL's the size of a room, and it's one big computer. And what we have now is many computers spread everywhere and communicating with each other. And so that completely has changed how we look at things.
You know, if you walk through the museum behind us, one thing that jumps out at visitors is the amount of memory stored on these large drums that, for which there was so much excitement back in the 70s and 80s. Like, you know, 64K on this massive drum, for example. And I often thought over the years of, if you just get a little graph by time of what the average person in our society, how much memory are they carrying on their bodies right now? You know, how many people are carrying less than a gig of memory on them right now in this room? I mean, probably nobody. And for me for those words that I just uttered to a large audience, to have, if that was heard, just that phrase, 15 years ago, people would say, wow, where are things going, just from that phrase? The reason I'm mentioning this is because, and to resonate with Peter, just resources alone, our current laptops are the supercomputers of 15 to 20 years ago.
One of those areas that they come together is machine translation. So right now I could use my Chrome browser or pull up my mobile device and hit Google Translate and surf the web in 58 different languages. I noticed I was looking at Google stuff, and you can translate into Yiddish, Welsh, Latvian, Swahili, Hindi. Here we are in Silicon Valley. There's buildings of Google all around us, but I don't think that there's a building full of English to Swahili translators, nor the other way around. So how is AI sort of under the hood figuring out with the big data sets how to do this translation?
That's right. So the field of translation has changed, automatic translation. And 20 years ago or 30 years ago, the way you did it was by trying to hire these experts. You go out and you get linguists, and you'd ask them, write down the vocabulary, what word means what word, write down the grammar rules, what's the grammar in English, what's the grammar in Welsh or whatever, and then somehow figure out how to translate between them. And that was a lot of work. And then when you were done, you had one language pair. We have 58 times 58 language pairs. That's quite a bit more. So you couldn't reasonably do that in the old-fashioned way. So what we do instead is say, well, let's just learn from examples. So let's go out and gather an example of here's a sentence in English and here's a sentence in Welsh. And now, if somebody asks me exactly that same sentence, then I'm done. All I have to do is look it up. I've seen it before, and I give you that sentence back. Now, of course, that's not going to happen very much. Instead, what's going to happen is you're going to ask a new sentence that I've never seen before, but I've probably seen some of the phrases before. And I can say, here's a 3-word phrase that you're asking me for. Have I seen that before, and what does it line up with? Now, how do you figure out what it lines up with? I guess you can see an example of that if you go to my course, and there's a short video, and in 3 minutes I can show you how to do that. And the example I use is a Chinese menu, and on the left-hand side there's Chinese characters, and on the right-hand side there's English phrases, and each line is a separate translation. And I don't know what any of the characters mean, but I can say, hey, you know, on the right-hand side, here's 10 English phrases in a row that have the word soup in it. And on the left-hand side, oh, here's 10 Chinese sets of characters, and they all have this one character in common. Maybe that character means soup. And then you cross that off, and then you say, well, how about the word chicken? Chicken's on the right appears in these places. On the left, it appears as these Chinese characters. Probably this Chinese character means chicken. And that's basically what we do. It's like doing a jigsaw puzzle. You figure out one piece, this word corresponds to this word, and then there's only so many pieces left over, and you keep doing that until all the pieces fit together, and now you've got this vocabulary. You know, this word or this phrase corresponds to this other one. Now, in the old days, as we've talked about, we thought of AI as being a logical system, and you'd have to say, what's the translation? Is it right or wrong? Now we tend to think of it in terms of probability. So we don't say there's just one translation. We say for this word, 80% of the time it meant this, 10% of the time it meant something else, 5% of the time it meant something else. And so we have lots of possibilities. And then the process of translation is there's this offline step of learning what words correspond to what words in a probabilistic way. And then when I get a new sentence that I want to translate, I just go through, look up the probabilities, and then there's a clever way of deciding how to maximize the probability, and I spit that sentence out, and I'm done. And all I've had to do was gather up these examples, right? In this case, I had to go around to a bunch of Chinese restaurants and pick up some menus. And then I could build a machine translation system, and that system didn't care that it was in Chinese. So we've built systems where we have nobody on the team that speaks the language, and yet we're still able to build a translation system.
For machine translation, some of the early boons to that research were finding generally aligned large bodies, or as I call it, corpora of text. You heard a small example of the menus, but for example, a classic training set was the Canadian parliamentary proceedings, which had to be in French and English. Right. It became a really great source of learnings. An interesting aspect of machine translation, which also is leaking into other fields and is an interesting challenge problem in itself for theory and practice, is this whole notion of transfer learning. So the idea, not just among languages, but how do I learn something about some particular aspect of the world, and then take that learning and apply it to some other portion of the world I haven't trained and tested on before. And this idea of whether it be going between mapping to new languages or new problems, starts pushing up against this notion, again, that Peter mentioned earlier, of intelligence in the open world, where you're faced with new challenges and new problem instances over time, and want to use techniques, methods, and knowledge, and maybe intuition and wisdom even in some of our systems, we like to say that reason under uncertainty, to make it through the world and be successful.
We were talking in the green room, and one very uncertain world is the ER room. You wear an MD hat as well.
Yeah.
And you've been working on predictive models in the ER room, of all places.
So, my dissertation itself was on time-critical decision-making for a bounded rational computer helping a trauma care situation. So we were just talking in the green room again. I was just back in Washington, D.C. on Thursday last week, spending time in a large urban emergency department where we have a project going with collaborators, one of which is to, which I think is a very interesting one, is to figure out when a patient who's just discharged from the emergency department will likely bounce back to the hospital within a few hours, often the standard is 3-day bounce back, and be admitted to the hospital with a serious illness. And we have built from large amounts of data, over 10 years of data from that hospital, predictive models that predict quite well these probabilities. I was sort of reflecting that one challenge is to have doctors actually use these systems, because doctors are very confident in what they do typically. And so we built a very special model for overconfident, or maybe just regular confident doctors, which predicts that the patient that they're discharging right now will bounce back to the hospital and be admitted with a serious illness within a few hours with a diagnosis that's nowhere on the chart currently. And would they mind looking? Would they want to look at it and see what the computer has to say about that? And so that kind of a model, a predictive model, gets physicians thinking out of the box a bit, and as the computer aids them with understanding and interpreting many years of data that goes beyond what a single person could understand, even with training and experience.
Another area of massive data that both Microsoft and Google are working on is traffic. And it's pretty amazing now. You can open up Bing or Google, and all of a sudden you know that there's a trouble area ahead and could potentially reroute. There's AI going under the hood here, I'm imagining.
So I can mention a little bit about work my team has done in that space. I thought Bay Area traffic was bad, but if any of you have ever come to Seattle at rush hour, you'll understand what happens when you have a very caring community that fights expansion. Meanwhile, everything expands except the road infrastructure. And so it's like hardened arteries that don't really respond well to pressure. So in Seattle, I personally got excited about understanding traffic better. One of our projects was called ClearFlow. It was codenamed ClearFlow, where we basically collected about 6 years of data. We just gave out at the time, before GPS devices were prevalent in cell phones, we gave out devices to Microsoft folks and their spouses, and just collected data on flows of traffic around the region. This grew into a system. I used to call this our Manhattan Project in machine learning. Our PR folks said, call it your moonshot. Okay, so
Nice.
Our moonshot in machine learning to basically predict every road speed in a greater city area, not just roads that are being sensed, like highway systems like in the Bay Area or Seattle and other major cities, but every single road. So do transfer learning, generalize what you know about roads to road properties and topology. And this ended up being evolving into a product effort that's now how you get traffic-sensitive directions and traffic-sensitive predictions on Bing Maps and on the Windows mobile phone. I hate to sound like an advertisement here, especially with the computer here.
Works on Google.
But it's been a really exciting project, because it basically says now that you don't have your naive GPS device that says traffic sensitive take you off 101 and onto a side street when 101 is blocked, because it just assumes that the side streets are just fine in those situations. It turns out that it can be worse. So we want to reason holistically about a whole city, and that was very exciting for us to do with machine learning.
I should say, in addition to the machine learning problem of understanding the data and how it's changing over time, there's also the static problem of how do you get quickly from one location to another. How do you plan a route from here to New York? There's millions of steps along the way. I see we have in the audience Peter Hart, one of the originator of the earliest algorithms to do route planning. And so that's no longer considered an AI problem because it's so well solved now, but it has its roots in AI technology.
I say Peter was just incredible contributions in the area of decision-making under uncertainty, inference, and I think the A-star algorithm is really plays quite a central role in thinking style and how we solve large problems. As a reflection, some of the directions we're going in machine intelligence are tools along the lines of, how do I face a massive search space or some massive complexity in a tractable way where I can make some sense with methods that might be not exponential but polynomial time that don't grow as fast as the size of the space. And we're seeing some magic showing up in this realm in computer science, in AI research, including ways to do simulation or sampling of spaces where you can start understanding the space by probing it with little spotlights. And just, to give you a sense of the science now, the idea is the world such that even in complex places we can sample and make sense of the larger whole without ever seeing the larger whole?
Peter, before Google, you were at NASA, and if you take one of these AI systems, put them in a box, and add some robotic arms and some sensors, all of a sudden you have a interplanetary probe. Talk a little bit about robotics and how adding interactions with the world and these AI systems is evolving.
Right, so I think that's robotics is another area where there is all this uncertainty. So we were able to do some work. I was down the street from here at NASA Ames, and we were working with the Jet Propulsion Laboratory on the control for the rovers. And we had a mission on our own, where the Deep Space One mission, where we actually had an AI planning system on board. It's the first time that had been done. Normally, spacecraft are controlled from the ground, and every single step of what the spacecraft done is radioed up to it. We did that on board, and then we inserted a fault into the system, and the AI system planned around that and recovered. So that was demonstrated, and we thought from there, well, now it's a simple step. We'll immediately put that in all the rovers, and they'll take off from then on. Turned out it wasn't that simple, because the mission controllers are deservedly very conservative. Right? And they all said, well, we love new technology, and we'll use any new technology that's been proven on 3 previous missions. So you can see there's a little bit of a chicken and egg there. Yeah. And so rather than saying, your system worked once okay on a technology mission, now I'll just adopt it, they were more conservative. And so what we ended up doing was taking our automatic control systems and putting most of the functionality on the ground rather than on Mars. And so what we could do then is give to the scientists and engineers a system where they could do what-if scenarios. And previously, Mars rovers work on a daily cycle. Mars day is about an hour longer than the Earth day, but since they're solar powered, they sleep at night, and the people on the ground plan what it's going to do the next day, and then they send up the mission and they operate for a day, and you keep repeating that cycle. And what we enabled the planners on the ground to do was to be more experimental. If the hours that they had to plan the mission, they didn't have to spend the whole time saying, is this going to work? Is this something that the rover can execute? They were able to say, well, what if? And then in a few seconds, rather than a few hours, our system could say, yes, the rover can do that, or no, the rover can't do that. So it was still a human in the loop who was making the final checkoff to say, yes, we can do this, but we were enabling them to do more. And now, as the missions progress, we had a very successful mission, long-lasting mission on Mars, and now there's another one on the way. I think they're landing in August. And each time there's been more and more autonomy on board rather than on the ground.
But here we are on the stage, and I can raise my eyebrows, I can gesture, we can smile or frown. We're communicating long before we're talking. How is AI and robotics trying to figure that out?
Well, I have to say that's you're touching on a topic that's central on my team now at Microsoft Research. If you went to my webpage, you'll see about 5 or 6 of my recent papers with colleagues is about the topic of how do we bring together multiple components developed in the AI field and push on weaving them together to build a system that could have a conversation of the sort that Peter, Tim and I are having right now, with all the nonverbal gestures, notions of gaze, engagement, even understanding when it is someone else is going to finish talking so that you don't overlap and so on, even what how to interpret the words into meaning as well. So I think it's one of the grand challenges. Again, when we sit in a living room, this is kind of a living room like environment right now, it's hard to understand how deep the intelligence requirements are to have a fluid conversation. Yet we do this in such a natural way. We don't reason about the computational foundations of what it might take. That's the kind of reason I think that Herb Simon was not thinking about when he said we'd expect to be doing some of the work of human beings very shortly in the 1960s. It's a grand challenge, and it often takes what we call integrative AI, as I mentioned, bringing together perception, learning, decision-making, vision, and I often like to say that on these projects, one thing we're pursuing is not just the assembly of copying together of multiple pieces, but new principles of integration of these components where the whole might be much greater than the sum of the parts. We understand something about the integration of these pieces of intelligence that underlie these kinds of rich behaviors that are so fluid for people.
So I think we always want our computers to be able to understand us better, to see not just what the words are that we say, but the intonation in our words and our body language and so on. That's always good. I think sometimes we want computers to be able to mimic that behavior, but sometimes we want something completely different. And to just try to say, well, let's have a computer that has a face, whether it's a robot or an animated face, often that doesn't work. That's not what you want. There's this notion of the uncanny valley, meaning if you get a robot that's almost like a person but not quite, it's really creepy. Whereas if you get it so it doesn't look like a person at all, that's often much better. And so you want to figure out how to build something. We also know there are cases, so another problem is the person you interact with has to have a model of how the computer works. What can it do and what can it not do? And if it looks like a person, then you want it to act like a person. And if it doesn't, then you're upset. If it looks like a dumb computer in some way, it's easier to get a model of where its limitations are. So that's part of it. And also of what your social interaction should be. So, I've been working on this education stuff. And one of the things Salman Khan pointed out to me is if you're a human tutor talking to a person one-on-one, which is about the best method we know for revealing knowledge, if after the tutor explains something 3 or 4 times and the student isn't getting it, the student tends to say, oh yeah, okay, now I got it, because he's embarrassed to keep being ignorant in front of the tutor. But if you do that in front of a computer, and the computer presents itself not as a human, but as a machine, then the student is perfectly willing to rewind the video or replay it 5 or 10 or 15 times, whatever it takes. And he doesn't feel like, oh, I have to prove to this computer that I've learned it and we can move on. So sometimes you don't want to imitate humans.
In this realm of human-computer interaction, there's a notion called complementary computing, where someday AI systems will augment our abilities in a very fluid way with a mix of initiatives. So imagine there's a problem sitting in front of a human being, and an intelligence is working with you, a machine intelligent assistant, collaborator, and it looks at that problem and it understands the parts that how to break it up into pieces, such that the parts that you'd best handle, the human being, are over here, and the parts that the machine, can handle are over here, and we're going to communicate that very quickly with some sort of a language and work together in a very collaborative way. There are simple examples of that now, but I see that as one big direction for machine intelligence is as general augmentation with communication and understanding as to who does what at any moment.
You're both head of some of the great research institutions in computer science. What are the big problems that you're working on? And how do they apply to sort of applied sciences?
So some of the big problems that are being worked on now in my lab and Peter's labs and other groups at universities include causality. How can we take data and reason about causality in a way that a deep scientist might probe causality? A is not just associated with B, but A is causing B. How can we learn that automatically? Or to see A and B that you thought were related and where A looked like it was causing B, but there's a hidden variable C that's causing both. We're now developing models and theories for doing that automated science, which is a very big, grand challenge area, which will have very big implications for our civilization. And I'm very optimistic that most, if not all, great discoveries, astounding discoveries, will be either by computing systems or with the deep assistance of computing systems over the next several decades and beyond. Another big area for us is, I mentioned before, transfer learning, but we use this notion of open world intelligence to really hit hard on this idea that Peter mentioned right at the outset of our session. What are some principles by which a system can look out and understand that its mind, its abilities and competencies are not deep enough and broad enough for the complexity of the environment that it's immersed in, and understand explicitly that it needs to learn and be on a gradient all the time, and to perform what we call lifelong learning. And we have some papers and some technologies on that front right now, but it's slow going and a big challenge.
So those are all good ones. Let me throw out another one, which is the object recognition problem. So given a picture or a video, what are all the things in it? Now, we've solved special cases of that. So you can buy a $100 camera now, and it'll put a little green rectangle around all the faces. But we've done that by very carefully analyzing what do faces look like and building in that one solution. Now we'd like to do it for every possible object, to take any video and say, what are all the things in it? Now, if you take a YouTube video, usually the answer is kittens. It's a universal. So we should be really good at that, right? Because we have a lot of data to learn from. We've got these millions of videos, and they've got a caption or a keyword that says cute kittens. And so we should be able to, just as we did machine translation, we should be able to go in and say, well, what's a kitten? Well, that's a little blob that looks like this in one frame, and the next frame it looks like this, and here's all the possible ways it looks. And then once we've gotten that, now we can address the other things in the image. So you subtract out the kitten, and you'd say, well, this is a scratching post, and this is a floor, and this is a wall, and this is a sky, and start to put together a catalog of everything in the world.
Let's look ahead a little bit. So in 10 years, 50 years, how far are we away from human intelligence? Just take a gamble.
Well, first of all, I object to that, because I think that's a low target to aim at.
All right.
Right? Because certainly there's lots of things already that computers are much, much better at people at, right? If I want to take the squares of the cosines of a long stream of numbers, I wouldn't want to aim at human level performance. Right? Awesome. So there's many things we can do better. If I want to memorize all the pages on the internet and choose one that best matches some keywords, I don't want human level performance for that. So there's things we can do better, and there's things we can do worse. And I don't want to duplicate a human. I mean, I know how to duplicate a human. I have 2 of them, and they're in high school, and they're doing great. So we don't need more of those, but what we need is a better partnership. We want to be able to say, what is it that humans can't do that computers can do better? Now, part of that may be that the computers want to have some basic competency at the human level in order to interact with us better. But the goal shouldn't be human level performance. The goal should be a superhuman partnership.
You've mentioned, like, if our grandkids are going to the airport or going to a doctor's office, what might their experience be different? Or what might they take for granted as we take mobile devices?
I think Tim is following on a discussion we were having. So I was describing that by my door at Microsoft Research, we've had several years now. It's one of our focal projects to build an assistant that's an admin with competencies that a human being would have, and the reaction we get from people walking to my door is one of people are astounded sometimes when it knows their name, and it makes eye contact, it talks with them about where I might be, it goes across the network and figures out how long it'll take me to get there, why I'm late, and with an apology, and should they get me a message. So we're starting to see services that are actually breaking through this uncanny valley that are working in a very complementary way with people and with groups of people, which is another interesting challenge, multi-party we call it, such that I suggested that our grandkids, maybe great-grandkids, won't find it out of the ordinary to walk into an airport and have a system that, sort of on a video screen that's kind of like a person that checks in, that says, oh, and is Zachary, is that your son? And he's with you, right? And that bag's a little bit big for the compartment, I think, over there, and really starts to do things we often would have a sense that people would be required to do. And there are many things like that that we can make as challenge problems, typically of integrative AI, and start pushing on. But I do agree with Peter that this idea of complementary computing with mixes of initiatives really has great promise for extending and expanding our abilities to achieve goals in the world.
Peter, how close are we from unmanned cars, Google or otherwise?
There's a mix there of a technology problem and a sort of societal problem of what can the cars handle and what can society handle? And so the cars are doing pretty well now. We've driven 100,000, 200,000 miles or so without a problem. And occasionally we have to shift control back to the person in the driver's seat. But most of the time they're under complete autonomous control. So they're doing great. I think they're probably right now about at the level of human drivers, which again is not that high a barrier. Right? So about a million people a year worldwide are killed in car accidents. So, but the problem is, if we cut that in half, we wouldn't get 500,000 thank you letters. We'd get 500,000 lawsuits from the other side. And so we've got to figure out, as a society, how do we want to deal with this? What can the cars do and not do? And then, and we also have to make the machines better, make it cheaper. So right now we have these cars, but they have extremely expensive sensing devices on them, LiDARs and radars and so on. So you got to get that cost down. And then we also got to figure out some way to deal with the user interface. So right now, we're driving the cars, it's under complete automated control, but there's one guy sitting at the wheel ready to take over at any second, and there's another guy in the passenger seat monitoring the computer to see if it's doing the right thing. And if anything goes wrong, they immediately spring into action. And if you sell this as a commercial product, the driver is not going to be sitting there alert. He's going to be sleeping or reading his email or whatever. And if a red light flashes, how is he going to take over quickly? We haven't quite solved that problem yet.
Yeah, I have to say that as someone who lost his mother to a car accident during my grad school days, and a few weeks back, some very close family, actually a whole family, Palo Alto family that was killed in a tragic accident while on a camping trip. I have to say that AI has deep implications for reducing collisions, even well in advance of completely autonomous driving. We should not be tolerating these number of lives lost to transportation, far more than our wars that really occupy our minds. 35,000 last year fatalities in the U.S., many more terrible injuries, and then of course the worldwide problem. So I think we can do a lot there, and I expect a great deal there from our community.
What do you think are the top 5 problems in AI in this century, or maybe just one of the top challenges that we're trying to solve that's not yet been figured out?
Well, I guess you could answer that in 2 ways. So one in terms of the application areas, and so like I mentioned, the object recognition problem, and then also in terms of the underlying technologies. So I think, and so let me answer the latter one. And I think there's a couple things that we don't quite do right yet. And one of them is doing hierarchical reasoning. So we can do generalizations, and Eric talked about some of those, and if you have a data set, we can find the best generalization for that data set. And you're used to doing that. If you see, even in your high school science experiment, you have some plots, there's X values and Y values, and then you draw a straight line between them. That's an AI system that's making a prediction. Right, and so we can do that with the raw data, but what we really want to be able to do is do that at multiple levels and say we observe the world and we make some prediction at that level, and then we make some generalization at a higher level. This isn't just the little data points, but this is what's going to happen. So you could go from driving a car from what image do I see in front of the car 3 feet ahead of it to what road am I on, to what route am I on my way to New York. And you don't want to plan out your whole trip to New York at the level of inch by inch. You want to have a hierarchical system. And we aren't very good at transferring from one level to the next. So I think that's one. I'll let you take the next one.
Well, I think the phrase common sense reasoning is actually a topic, because there are several subtopics there. But let me just say for now, mastering what we consider to be common sense reasoning is a big grand challenge in AI. If people want to do a little bit of reading, there's a fabulous piece of work by Patrick Hayes from a couple decades ago called The Naive Physics Manifesto, where Patrick just said he got back from the Piaget Institute, a study of kids, a Center for Study of Children's and Minds in young people in Europe, in France. He got back and said, I want to just write down the logic and the inference you need to understand when a glass of milk falls over and spills onto a table, and to look at the challenges that required to encode that representation and the inference framework for a system to reason the way a kid might reason about a glass falling over and getting a cookie wet. This is a big grand challenge. Another grand challenge which comes into the same, which intersects with that challenge, is the open world learning problem. And I'll just, since we're sitting in this room here together and getting close to the end of the session, I'll bring up a big elephant in the room. A deep challenge is understanding what on earth's going on with consciousness. This whole notion of sense of self, being, experience, qualia, subjective states. We really don't know what's going on there just yet, whether it's epiphenomenal, whether it's something special, it's an illusion. Do machines that are this competent just happen to feel like I feel, for example? I think we'll get some answers along those lines over the next few decades.
How will we know? Will it be a Turing test type of thing, or?
Well, I should say that I've never been a big fan of the Turing test, even though I deeply, deeply admire
Can you explain
Alan Turing.
it for those who don't know?
People probably are quite familiar with the Turing test. Alan Turing wrote a treatise in 1950, thinking about, well, how would you ever know if a system was as smart as a human being? And I think he punted when he said, well, the system will, if I spoke to the system through a teletype machine and through a human, I really can't tell the difference when I ask any question I want and listen to a response. So he's giving sort of a behavioral argument. He said the only way we'll be able to tell if something is as smart as a person is through a behavioral set of probes and responses. I've never really deeply been satisfied with that.
Do you have a better one, Peter? What would be your test for intelligence of the next level?
I guess I'm going to punt, and I'm going to punt even harder than Turing did. I'm going to have a 63-yarder or something. I like the words of Edgar Dijkstra, who said the question of whether a computer can think is about as reasonable as the question of whether a submarine can swim. And so I think what he meant by that was that the answer to the question is really an answer about linguistics, and it's not about computers or about brains. And that in English we have this convention that most of you, we could do a show of hands, but most of you probably say, well, no, submarines don't swim, but airplanes do fly. But that doesn't mean that naval engineers think of things differently than aeronautical engineers do. That just means that's the way we chose to use those words. And in Russian, if you ask the equivalent of the word swim, that does apply to submarines. But the Russian submarines aren't built different than the English-speaking submarines. So for me, what really matters is what you can do. And maybe, I think Eric mentioned consciousness, and I think that's a fascinating topic, but I just decided I'm not going to count that as my topic. My topic is getting computers to do the right thing, and philosophers and psychologists can worry about the other problems.
There's a question about sensors and motor movements. I mean, there's been sort of a Moore's law of the miniaturization and the computational power in all the sensors that are around us every day. And you talked about data inputs before, and now not only do we have the language of the web, but hundreds and millions of images and barometric pressure, all these sort of sensors are out there. What does that mean for robotics and AI?
I think the incredible availability of low-cost sensing and the ability to network it and collect data from it that's come with the march of computing more generally, some of which is captured behind us in the current exhibit at the Museum of Computer History, is really fueling lots of innovation in terms of topics of machine intelligence in what's called ubiquitous computing or pervasive computing. New applications of sensing and optimization for example, making sure your vineyard is working at the optimal, is producing the right kind of grapes, for example. Understanding whether a driver is fatigued at any moment, needing help and assistance with driving, or maybe some more aggressive automatic braking. So there's an incredible world of innovation that's been stimulated by the availability of these sensors, typically network sensors.
So we probably just have time for one more question. What are you most optimistic about in the field of AI, whether solving real-world problems or helping advance the computer sciences?
I guess I'm optimistic about the kind of positive feedback loops of saying as more data becomes available, then we can start doing more with it, and as we do more with it, that creates more data, and it looks like we're on the right trajectory that way.
And in particular, I would like to resonate with Peter there, with applications to education, healthcare, the sciences, and our economy. I think we'll see that this kind of data to knowledge to action with a loop will really have implications for many aspects of our society.
It's a great place to end. Please join me in thanking our distinguished guest, Eric and Peter.
From smart medicines to self-driving cars, artificial intelligence continues to represent computing's brightest hope and biggest challenge. Explore the history of computing and you'll connect the past to the future. See you next time on the Computer History Museum presents Revolutionaries.